any further ado, Lisa, please take it away.
Thank you, Enrique. And yeah, my longest bio, so I don't have to introduce much about myself. So you can still see my screen, right?
Yep.
The little green
Perfect.
bar went away. Okay, great. Yeah, so as Enrique said, I'm with Phius. I'm associate director, and I really kind of the meat of this presentation are a lot of the main motivation behind getting into this topic was learning and really understanding how important building design, building operation is going to be in total grid decarbonization. Before kind of learning about electricity markets and things related to power generation and whatnot, I was in the building design side working with Phius, and it seems that they're very siloed, right? We have like building design, and then beyond the building, that's the grid. And I think there's really, really great opportunity to kind of combine those realms and really work together to kind of harmonize and communicate and reach goals toward decarbonization. And I just want to apologize in advance. I'm battling a cold, so I might mute and cough for a few seconds or something. So I just apologize in advance for that. Okay. And if anyone has a question, I'll try to keep the screen over here. You can raise your hand or just pop something out during the middle. I don't mind at all. So feel free. Okay. So I know this is a Passive House Vermont group, or at least was put out in a Passive House Vermont email, but I just wanted to kind of level set right at the beginning about what passive building is. It's just kind of the highest definition. So these are two different annual load profiles of buildings. You have a typical building on the left and a passive building on the right. And what a passive building is basically doing is using passive strategies. So that's insulation, air tightness, just a high performance enclosure, better windows, balanced ventilation with heat recovery, using that to reduce loads both annually, so the area under the curve, as well as at the peaks. So that in a nutshell, that's what it is. It's flattening loads and using passive strategies to save heating and cooling. So I'm just trying to kind of level set that definition at a high level. So I understand there might be some utility people on, but most of us don't think about where our power comes from. And, we flip a light switch on and, the power's there. And then if it goes out due to a storm or something, that's when we start kind of thinking more about what is on the other end of that, meter. So we're gonna start by talking a little bit about the grid and the current operation of the grid, where that's going, and then how building fits into this. So the grid, someone coined it to be the biggest machine on Earth. There's 3 different interconnects. There's the West, East, and Texas. They're not connected. They operate same frequency, but slightly off from one another. And different regions of the grid are operated by different ISOs, or independent service operators, or there's another name for some of the other regions that aren't ISOs. So up in Vermont, you guys are the New England ISO. It's a really complex process what's going on with the utility grid, but I think a lot of it's actually fairly antiquated in the way that it's working relative to the technology that we have today. So the current, just at a high level, current electric grid infrastructure is you have generation, you have transmission, high voltage transmission, and then lower voltage distribution, and then a customer load at the other end. And it's unidirectional power flow. So one from generation to load. And if the customer load increases, the power generation must also increase. And this is kind of just how it goes. The generation must be built in order to meet the customer load. They must have enough capacity, and it must be able to respond to continually supply power to these buildings. And in terms of resources that we have on the grid, this is nationwide. We have about 35% natural gas as a fuel to create electricity, 23% coal, 20% nuclear, 15% renewables, and 7% hydropower. And we know that renewables will be the fastest growing source of electricity generation, or we hope, at least we at Phius hope, for greater decarbonization. And the loads that the grid sees are fairly predictable. The load that the different ISOs or different, I guess really e-grid regions need to balance are fairly predictable. So in winter, There's a base load, there's an intermediate load, kind of when the day starts, and then a peaking load, which in winter is just heating up buildings in the morning, and then kind of that late afternoon, evening peak. And then in the summer, you have, again, a base load, an intermediate load, and then one peak in the middle of the day. And these loads are met with different types of resources, different generation resources. So coal and nuclear and maybe some renewables are used to meet baseload. So it's this is mostly because these resources are constrained to constant output. So it wants to be set and say, I'm delivering this amount of power and I cannot change that. Intermediate load is met by what is called load following resources. So some natural gas combined cycle, maybe some renewables. So when that load increases, that resource is increased to follow that load, right? To ramp up. And then the peak load is met some by load following resources, but also by peaking plants. So there's natural gas peaker plants, or maybe hydro in the form of storage that's dispatchable to meet that peak load really quickly during the peak. And in terms of the capacity that we have in the US grid right now, there's about 2.5 to 3 times more generation than what's used annually. Sorry, not more generation capacity than what's used annually. And what that really means is if everything we had ran all out all the time, it would generate 2.5 times to 3 times more energy than we actually need over the course of the year. And that's because of this peak. So the system has to be sized to meet that peak at that critical moment. And with building design, I assume many on this call are related to building design or operation. We kind of understand this from the point of, let's say, a heating system size. You calculate a peak heat load based on one critical, condition during the year, one critical climate condition, and then you also add some redundancy on top of that to make sure that load is met. But this is happening at the scale of the utility grid to make sure that peak load of the grid can be met. And as the peak increases on the load, or as the grid load increases over the course of the day, more and more expensive resources must be called upon, because the resources, the generation resources essentially bid into the power market at a certain price. So you start with the lowest cost and then increase over time. So that last kind of kilowatt or megawatt in this case of power is the most expensive one. And another way to kind of look at this is on the right chart here, as the demand increases, as this vertical line goes to the right, the market price increases, the horizontal line. And it's not linear, right? Like after a certain point, that next resource might be more expensive. And that's when you get into these peaking plants and these really expensive resources that happen when the demand is really high. And utility pricing, generally we see most residential customers, or at least see flat rate pricing. It's more of like an insurance policy almost, that you're not subject to the vulnerability of the actual cost of the market electricity. But real-time pricing is actually variable. So the utility is, I'm sure many on this call understand, the utility, the actual pricing to deliver electricity at any moment is variable, though most consumers are paying a flat rate for it. There are, I should say, there are a fair amount of markets that use time of use rates, or you can, even in Chicago, you could say, I want to use the real-time pricing, but generally we see flat rates. And because every hour, every moment, the electricity being delivered to a certain region or a certain building is a different mix of generation resources, there's a different marginal carbon emissions associated with that, which means that next kilowatt hour delivered has a different emissions rate than a different hour, because it's a different grid mix, right? It's a different mix of resources, and every resource has its own carbon emissions associated with it. So this is for Chicago. This is from a source called Watt Time, where they have a large database of different grid regions where you can see the actual marginal emissions. It's from past data, so they don't project future as far as I know. So this is from Chicago in 2019, and you can see the months of the year and the hours of the day. And what are the emissions happening at that time relative to different times of the year. So the red hours are the really dirty hours, or the highest emissions, whereas the green hours are the lowest emissions. But even with Phius, if those that are familiar, we just say every hour is the same. When we talk about energy, we look at annual energy, we multiply by static source energy factor, and every hour is the same. And if you look out at what Phius is using right now for the 2050 grid electricity source energy factor, we're using 1.8, which is the average right here in the middle of the line. Whereas this is actually what the projected hourly source energy factor is for 2050, that kind of squiggly line across. So it's quite variable throughout the year, although again, a lot of our accounting methods look at a single flat rate. So we're going to look at a couple different curves from the New England ISO and the California ISO. So this, I went in on the New England ISO website, and you can grab demand curves from any day. This is from July, earlier this year. One moment. And you can see kind of the forecasted rate, the actual rate, and what cleared the market. This is the summer day, so that you have the afternoon peak. Sorry about that, guys. And then you can see the generation resources needed to meet that peak. So you kind of have your flat line, base load, nuclear, renewable, hydro at the bottom, and then your load following natural gas. So this is day after day. You can go in and go to the website and look at the day before. I usually like to update this to yesterday. So it's, you can tell it's not a special day. This is just a day in this year. And then this was new to me in this year, where they added what they think the actual load on the grid was, including the estimated behind the meter solar energy, which means that this is what they're estimating was the actual load of all of the buildings combined. But they don't actually know what those buildings were using, because there was PV on the roofs of these buildings that was being used in the building before it actually hit the grid load. So it's offsetting the use of this, the energy use of this building. So the grid never actually saw that load. So they're estimating, but because it's behind the meter, there's no actual exchange of data with the utility to understand what that load was. And the grid is changing. So we kind of already saw that the grid is changing a little bit, but in that last slide, but there's electrification. We know there's EVs, vehicle to grid, charging, heat pumps, things with electrification we'll talk about more. Decentralization. So we have energy efficiency, PV, storage, microgrids, and demand response, which we'll mostly focus on. And then digitalization. So opening up, the technology that we've experienced in the past couple of decades that is being applied now to the electric grid, whereas the electric grid in many areas hasn't been updated in quite a while. So to look at kind of the best example of a new grid or a most changed grid, we look at the California ISO. So same day in July, looking again at the day ahead forecast and the actual demand on the grid. And then this is the renewables trend in California. So they have really high solar penetration. And then this is the net demand on the grid. So this purple line is the load that the grid actually has to meet. And I don't know, 10 years ago, probably the duck curve came out where it talks about the ramp, which I'll show. But this is happening day after day, where the ramping period, either ramping down or ramping up for the grid, is a challenge due to the limitation of the resources that are available to meet that load, whether it's ramping up to increase, power output, or ramping down to turn down those resources. The other big challenge that's happening is the transmission lines aren't upgraded quite sufficiently to carry the load. So if you have a central solar PV system, the lines there's congestion on the lines.
There is a question, Lisa, if you want to answer it, from Andy, what is the shaded area on the last graph?
Sorry, I didn't think the coffee would be quite this bad. Yeah, so the shaded area is they're highlighting the 3 hours with the greatest ramp. So this is like the greatest incline in that load that must be met by the grid. So they highlight this, I think, every day in these reports, because this is the challenge that the grid must be basically able to meet. They need enough resources that can increase output quick enough to meet that ramp, and that's the challenge. So this is the ramping portion of the day, and it aligns with also when the sun goes down, right? So it's right here. So the renewable resources that were available during the kind of the sun setting hours fade off, and now the grid must make up for continuing to meet this teal line at the top, which is the total demand curve of the building, or of the grid region.
Lisa is fighting a very bad cold.
I'm sorry, I haven't tried to talk this long yet. So I wasn't quite sure.
Just do whatever you can, no problem. Don't worry about it.
No, it's no problem. I'll just keep muting if it's okay. Okay, so the other thing that's happening again is the transmission congestion. So the big pieces here, that's the same day in July, is the economic local, which means that they're mitigating local congestion. So the least cost energy, which is at the end of the transmission line, the PV, can't get to the load because the transmission line can't hold it. And then the other curtailment that's happening is due to mitigating system-wide oversupply. So there's a lot of excess energy use or energy being produced during those times. So it must be curtailed because it can't be used. It either can't get brought to the customer or it can't be used. So when you see negative electricity prices, this is one reason this occurs. So here's kind of a graph of where we're looking at the US grid going by 2050. So on the left side is generation. So that's the actual terawatt hours in this case that are being produced and are being consumed or produced by the different generation capacity. And on the right is the actual equipment or infrastructure. So on the right is kind of, you can think of it, or I think of it kind of as the cost of this transition, right? The actual new infrastructure that's required. And on the left is really like the emissions associated with it. So what you want is for the new renewable infrastructure to make up a good portion of the actual generation, so that the emissions associated with the total energy use that's happening to be lower. And one interesting point on here is you can see this light purple capacity on the right. That's the natural gas combustion turbine. And you can see the capacity is a pretty large piece of the slice over here on the right, but the actual generation from it on the left is very small. And that's that peaking plant. That's that expensive resource that we have to keep online, spinning reserves in order to meet the peaks on the grid. So that's a lot of the reason for spikes in utility prices. And that doesn't seem to be going anywhere with the projections from NREL right now. And I should say this came from their Cambium model, mid-case scenario. So it's basically looking at, I think this came from 2020. So every policy that was in place as of 2020, they just assumed that played out. They didn't assume anything new was going to be signing on or anything, just everything that was already initiated in 2020 would play out. So they have other more optimistic cases and less optimistic cases for this grid mix. So really looking at this whole grid decarbonization, like I mentioned in the beginning, we need to think beyond the building. How do the decisions at the building scale impact the decisions at the grid or utility scale? So we're going to go into some changes and challenges. Okay. So when thinking about the grid or utilities, it's usually talked about in a supply side and a demand side. So supply side is the generation resources and the demand side is the building load, the load that must be met. And that's starting to get a little murkier as buildings are, adding PV on the roof or adding energy storage. So is energy storage supply or demand? It could be both, things like that. It's starting a little bit murkier, but in general, it's kind of two sides of the coin. And right now we have more control of the supply side. The utilities operate these generation resources and dispatch power when needed. And the demand side just uses what it needs, right? We have less control over what the buildings are actually doing. And I think there's going to be a fundamental switch that needs to happen. We know that the supply side, we're losing a little bit of control of the supply side as we add more wind and solar and more intermittent renewable resources into the supply side. So we need to get more control of the demand side. That's kind of what I'm going to talk about. The other big thing that's happening, at least I think it is with Phius, we see this all the time, is net zero buildings becoming almost commonplace in different local policies and goals for organizations or different jurisdictions. So net zero buildings is becoming more commonplace. There's electrification happening of both buildings and vehicles. I'm going to try to focus on buildings here. And then we know that our dispatchable fossil fuels generation is shifting to variable renewables, like I was just talking about, the more control to less control. We're turning off old fossil fuel-based plants and turning to more renewables as our power supply. So all these things are happening at once, and there's a lot of different, I guess, players and pieces, and there's a lot of different overlap in terms of solutions. So when I talk about net zero, I apologize if everyone on the call knows this concept, but just quickly to define it, net zero in most definitions is a building, or a net zero building in most definitions is a building that consumes as much energy as it produces over the course of the year or annually. So a building has, let's say, uses 1,000 units of energy. It must also produce at least 1,000 units of energy over the course of the year. This is a great goal. It helps, bring a little more independence to clients and get more widespread renewable energy, but it doesn't mean that there's no impact. It doesn't mean there's no reliance on the grid. It doesn't mean there's no emissions. Absolutely does not. So we're going to look at two different kind of load profiles or flavors of net zero, I think of them as. So if we had this multifamily building in Chicago, 32 units, 96 occupants, 35,000 square feet of floor area, and all electric. So this is a DOE prototype. It's not a real building. So I'm sure some buildings in Chicago suburbs might look like this, but this is a prototype building. And looking at if you were to take this building to net zero with two different kind of baselines. So the first is just meeting code. And this was, I guess this was pretty old, I think 2012 code. So it was older study, but it's a renewable oriented building, which means it met the baseline code for the jurisdiction, and then it added PV to get to zero. So whatever that was, we call this renewable oriented because it first just met code. And that needed 290 kilowatts of PV, and the array is all south facing with a 10-degree tilt to fit more on the roof. It doesn't all fit on the roof, I'll just say that, but that doesn't matter. We're thinking of this irregardless of that. And then the passive building needed about half the PV, again, and this is a Phius certifiable building. So for the baseline building on the left, on the chart, the yellow is the PV output of that building required to get to net zero, and the blue is the building load profile. This is an all electric building. So this is the heating in the winter over here on the left and on the right. And then the summer load profile of the building in the blue here. Lots of daily variability. What you can see is how much additional output you have in the summer, right, from the PV that's never going to be used by the building. So that'll go into the grid and the kind of the mismatch here. And then when you look at the passive building, you can see the loads are significantly lower. This dark blue is hanging lower to the bottom of the y-axis. And then some peaks in the winter, right? And still mismatch, right, between solar and building energy use, but less because less was used. And then if you look at ultimately the peak of that building or what the grid capacity would be required for that building, you look maybe around 130 those kilowatts for the baseline versus maybe 80 for the Phius building. So remember, the peak defines the capacity or the ultimately the maximum power output of the generation needed to serve the building. If you were to look at this in one other way, kind of spinning it around this chart, January to December, we're saying this building load of the baseline building is being offset by this yellow load. So the blue lines are being offset by the yellow. And same with the passive building, a little bit smaller of a blue, more condensed, lower loads, a little bit smaller yellow, right? But they're not identical. The timing is off. And then if we were to zoom into spring day, April 15th, and October, fall day, you can see the baseline building on the left, the PV production is significantly higher than the building load. Whereas on the right, sure, the building load's a little bit lower, PV production is a little bit lower because the total PV needed to get that building to zero was less. It was about half, right? So the mismatch between the two loads is lower, or the two load profiles is lower because just less energy was used in the building, so less energy had to be produced to offset it over the course of the year. In the same case along the bottom in October. So what do we get out of that, right? So just understanding that net zero buildings that rely solely on PV to offset their annual energy use, whether it's passive or not, you still need grid support when the sun's not out. That's basically it. Without energy storage, you still need grid support. So net zero is a great goal, but it isn't the only goal, or it's not the end goal. There's more that we can do. But still, if you consider the passive case, we only needed only half of the reliability from the grid had to be provided because it used half of the amount of energy. So just thinking about the concept of net zero, it addresses how much. It's this amount of energy over a certain amount of time used and produced. Really, the total end metric could be net zero over an hourly or a minute basis, and maybe that accounting could be more correct. But right now we use annual. And on its own, that doesn't address two key concepts that help or further reduce operational emissions and facilitate more renewable resources or grid decarbonization. So that's really the goal of the Phius+ program, is to further reduce operational emissions, right, and allow for more renewable resources. So these other two key concepts are low loads. That's not baked into net zero, but it is baked into the Phius program. So if you start with Phius Core, Phius+, low peak loads taken care of, right? And that, again, helps further reduce operational emissions because we're keeping the peak down and facilitates more grid decarbonization. But it doesn't address timing of energy use. Timing is important. So if we're thinking about, again, the demand side and the supply side, when is energy being used? Does it align with renewable production? What emissions factors is that building's next kilowatt hour using? And then if it's producing energy, when is that being produced? Is it useful at the grid at that time? Is it going to be curtailed? What grid factor is it offsetting? Is it already offsetting a grid factor that's clean? Are you just adding more clean energy to the grid when it's already clean and excess energy that can't be used? We have to consider these things, but the concept of net zero on its own does not do that. Another big thing happening is consumers are becoming producers, and there's widespread solar energy, also called distributed energy resources. So I talked about the duck curve, just to touch on that briefly a little more. We looked at the California ISO graph earlier with kind of the belly of the duck and the shaded end portion of that 3-hour ramp. So this is, again, 10 years ago, 2012, that they started to see this happening as more solar came onto the grid. And what they're looking for is the challenge is the big net load change during these small ramping periods, these few 3-hour periods, a significant increase in load. And what's interesting is this is not just California anymore. So this is from Massachusetts, from the New England ISO, or actually not just Massachusetts, I'm sorry. The New England ISO showing, this is from 2014, their predictions for, by 2019, we'll hit the 3 gigawatts. So that's about here, this first green dot, and then keep going. So I looked at the New England ISO in April from this past year, and it is there. The duck curve is fully in New England in the spring months. So the top curve is kind of the actual load on the grid, or estimated, right? The actual load that the buildings are using. And then here's the net load. If you can see my mouse, because of the solar being produced. And then there's a significant ramping period in the afternoon or evening. Okay, so if we were to think back to the multifamily prototype that we saw before, the 32-unit Chicago building, and look at the baseline versus the passive building. And we're going to make each of those net zero with PV. And we're going to group them together, 1,000 of them in a community. And this is the day that the duck curve, we're going to look at a single day load profile, the day that the duck curve is typically demonstrated on, which is March 31st. Usually sometime in spring, low space conditioning loads, March or April. So this is March 31st for both of those buildings. And we can see on the left, the baseline building, as we make more and more of these clusters of buildings net zero. So first we have 0%, then 10%, 20, 30, 40, 50. The top of this line is if 0 of them are net zero. This is the load the grid sees. And if 50% of them are net zero with solar, this bottom green line all the way down here is the load that the grid sees. So this is, again, just taking those multifamily buildings and making them net zero with solar. And this is just if half of them are trying to be run based on, or net zero with solar alone. If you look at the passive building, you can see, again, this kind of the line following across the top, the green crossed over to the blue here. This is the load that the grid would have to supply without them, any of them being net zero. And then 10%, 20, as you move down this kind of array down here to 50%. This is the net load if 50% of them are net zero with solar. So in the baseline building, you can see there's significantly more ramp, right? Because more PV was needed on an annual basis to get to net zero. And the loads in the building weren't quite as smooth or as flattened. So the passive building has a ramp that's 3 times less intense than the baseline building. Remember, this is the same size building, same climate, serving the same number of people, just with different design strategies. First, the passive building reduced peaks in total energy consumption by about 50%. And that alone helped kind of minimize that ramp. So the passive buildings dampen that issue, but they don't fully eliminate it, right? So yeah, I keep moving for that. So the when will become very important. So if we think about another daily load profile and the time of the day, we usually say every hour is the same when we're accounting for energy use in buildings, when we're doing design of energy use or design for low load buildings. We consider it all the same, even though we know it's varying. So if we think of a building that has the same demand curve, that black curve, we're going to look at one case here with a conventional fossil fuel grid. The morning, or where the peak on the grid is lower, is generally the green hours, the cleaner hours. And as that load increases, it gets dirtier and dirtier because the whole grid is starting to peak more. So that's yellow, then some red hours, and then back to green as the load decreases. Maybe in a building like this, you'd actually want to shift more energy use to those green hours, right? To actually reduce more emissions associated with the building energy use, you'd want to move more hours to the green hours. So maybe the ideal load profile for this building would be this dark black line on the bottom. But for a building with the same exact demand profile, but if it's either has PV on the roof or in a grid with high solar penetration, the morning hours are actually dirtier. And as the sun comes out, the afternoon hours in the middle of the day and early evening are actually cleaner. And then it's dirtier as that peak, that shaded part of the graph, as that ramp goes up, it gets dirtier and dirtier. So in this case, you'd actually want to move more energy use to the middle of the day, right? We're trying to get more hours of the energy consumed during the green hours. So maybe an ideal load profile for that building would be this large peak in the middle of the day, right? But without access to this building, knowing what are the emissions on the grid or any sort of communication for the building load shape to change, same exact load profile with different supply sides has very different solutions for reducing emissions. So we want to enable the building loads to be smart and responsive to signals. So this is where GEB comes in, grid interactive efficient building. This concept's a few years old. The DOE is releasing, some roadmaps and early research on this, but this isn't a widely adopted kind of strategy or solution yet. But I think this is going to be absolutely critical to addressing the timing. So just a quick look at how this might work, or like a kind of schematic here. So the utility might have control over this grid interactive building in terms of some of the loads in the building, but they'd be defined through an optimization and control system. So the HVAC loads maybe could fluctuate, maybe lighting could dim, plug loads, maybe there's some critical versus non, PV storage, when is it best to store versus dispatch electricity or power to the grid, and when is it best to EV charge, right? So kind of trying to optimize this based on communication with the utility and the grid stress at that time. So a GEBS toolkit, very simplified. There's more to it, but there's load shifting and load shedding. That's what I want to talk about. So load shifting on the left is a load that has to happen, but you can shift it to another time in the day. So let's say running a dishwasher or a washer or dryer or something like that, maybe even space conditioning. You need the load, but you can change when it's happening. So in this left-hand scenario, you have the gray profile. Maybe you want to reduce that peak and add it to the morning because it's the greener hours in the morning, right? So focusing on when they're consuming energy as opposed to how much. And then load shedding is reducing energy at the peak. So this is just a load that doesn't have to happen and the building can shed it, or also demand response. And this is based on like a grid signal or that peak happening at that time of day. So for this, I generally think of space conditioning loads or temperature thermostat set points or lighting, dimming, things like that. So if we were to look at the grid scenario we looked at before, but look at it with GEB, grid interactive efficient buildings, and look at a time of high grid stress. So we still have the power flow happening from one end to the GEB customer load. The grid stress is high, so it sends a signal to the customer to reduce the load, and that's demand response. The customer can reduce the load, and then the grid stress can, either the utility wouldn't have to go up to that next peaking plant, or that next generation resource, or the cost would just be reduced for the customer, right? The electricity price is about to get very high. It's best if you can reduce your load at the time. That's demand response. The other kind of scenario on the other side of the coin is if there's low grid emissions. So at that time I was talking about in California, high renewable penetration, but it doesn't, let's assume there's enough transmission to get it to the customer. So there's power flow again going from the clean energy to the customer load, and the grid stress is low, but there's abundant renewable energy. So maybe the customer should actually increase their load right now if they want to, cheaper energy, lower emissions energy. And so maybe the demand response happens in the other way. Maybe the building is preconditioned. So maybe your space conditioning, say you're home in Vermont in the morning, or overnight, whenever the renewable resource is available, or in the middle of the day. So that you can offset some of the heating needed later in the day. Or maybe you're charging your EV, something that can happen at any time, really, based on the signal from the grid. So you can either take on more power at certain times or shed more at other times. And there's a big synergy between this grid interactive building concept and passive building. So passive building is kind of like the Yeti of buildings. If you think about the thermal enclosure, I don't know if anyone has a Yeti coffee cup or cooler, but I mean, it's amazing how long it can keep coffee warm or keep ice cold or keep ice not melted. So it's really like the passive building is very resilient to changes in exterior temperatures. So if you drop, the heating, drop out the heating system for a few hours in any of these passive buildings, it'll maintain comfort, right? Thermal comfort in the building. So it's really good at either shedding that load or shifting it, preconditioning the space. It will then maintain that space conditioning that was already given to the building. So it adds this inherent thermal storage capability to that GEB toolkit, which is just kind of another synergy. And when we think about renewables in the future. I think in the future grid, I think a lot of people understand that storage is going to be a key part of it. But I think it's often ignored that buildings themselves can be thermal storage capacitors. Like we often think about large scale batteries, right? But there's all these untapped resources with kind of the time constant of the building enclosure for these passive buildings that can be just as useful as electrical energy storage. So Phius+GEB, I put it in the name, but it's not a real program, so I apologize if someone thought they were going to hear about a real program today, but it's not a real program. It's just kind of my dream, where you take the Phius concepts, the passive building concepts, but then think further. Like, right, it might not need to be net zero, but you use Phius core, all the best practices of Phius passive building as a baseline. And then maybe you think about how much load can the building shed? How much can it shift? How much can it take on excess renewable power? Maybe I'll offset later. What are the critical loads of the building? How responsive is it? What are the generation energy storage components? So it's more like a piece or a key knob in the future grid rather than another net zero program. Apologies. Okay, getting into building electrification. I see the time. I'm gonna have to move a lot quicker. I didn't account for my water breaks. So just quickly, water heating has a huge potential. Water heater with this electrified water heater with a storage tank to act as an asset for the grid. And the same kind of thermal storage way that I just discussed. But I really want to talk about the passive building side. So I mentioned that the peak is changing. So right now, the entire grid the US grid peaks in the summer. And this is because the cooling systems are electric, right? So when the space conditioning loads are high, the grid peaks. And that peak is shifting to the winter. So, sorry, the grid peak that we talked about, the 2.5 to 3 times more capacity than we need, is all sized for that summer peak. But we're going to start to electrify buildings, electrify heating systems and buildings, I'm sorry, and shift that grid to the peak to the winter. It's going to be even higher than it is right now, all while we're trying to swap out, fossil fuel based reliable resources for these intermittent renewables. So this peak changing is really, really, really critical, or a really big deal. So we're going to look at kind of 2 flavors of buildings again: typical code baseline building in a winter, in a passive building. So kind of the same 2 flavors, looking at a winter day load. We're going to say the typical building has a peak of 4 and the passive building has a peak load of 2. This is actually being generous, especially somewhere like Vermont. You could probably reduce the peak heat load of a passive building by a factor of 3, maybe 4, depending on the building. But you can reduce the peak heat load by a significant amount by using passive strategies in a climate like Vermont or a cold climate. So we're going to look at these kind of played out. So if we look at 3 of these buildings, these typical buildings, coincident peak heat loads, their neighbors, let's say, the heating's happening all at the same time, the grid capacity required of the grid load is 12, right? 4 plus 4 plus 4 is 12. Now we make them passive. 2 plus 2 plus 2 is 6. So we've reduced the grid load by a factor of 2, right? You understand that. And now if we take the passive and we integrate this grid interactive building strategy using load shifting and smart technology, using the thermal storage enclosure, we can have the heat load happening at different times in the day. And now our grid load is 4, right? So just by implementing first passive to reduce the grid load and then shifting them around, we've reduce the capacity required to meet these 3 buildings load by a factor of 3. So now we're getting the microgrids, and I'll try to get through this in the 10 minutes allotted here. So we keep looking at this unidirectional power flow chart, one direction, generation, transmission, distribution to load. Microgrids, I'm not an expert on this, but it's more of a mesh network where there's interchange and interconnections between buildings and the ability to exchange energy between buildings. And just at a high level, the key components are energy demand from buildings with the grid enabled loads, so those GEB buildings, energy generation of some sort, storage of some sort. And then what's really critical is this central system, central energy manager optimization system. So on the left, you can kind of see a schematic of how a microgrid might work. She mentioned microgrids are generally connected to the main utility grid, but have a central point of connection. So essentially everything that's happening in the microgrid is happening in isolation. And then there's one connection with the utility that can either can transfer power in both directions. So within the microgrid, you can see the generation, the storage, and then the loads, right? So the microgrid manager, this optimizer, is really important. So if you think about the supply side, you have your generation. If 1 kilowatt hour is produced, where does it go? So this thing would think maybe if it's a time of low supply, it'll serve the most critical load in this microgrid. And that would be defined, like these things would be programmed into this manager. If it's a time of excess supply, maybe you store it or you charge another EV if they're not full. You shift a non-critical load of another building to use it. So maybe it, powers something on, or maybe you condition a space past its set point. So if you know you need to heat the building, you heat it a little bit more at this time and then let that float later when less energy is available. On the demand side, when a building adds a new load, how should it be met? So it also has to determine this. Is there renewable energy available for it? Is there storage you could dispatch from your microgrid? Is it a critical load? Does the building need it right now? Or does it come from the main utility grid? So there's a lot of complex things going on here that this microgrid manager must assess. Oh, and this is my dog Flynn asking about the winter peaks. So what about the winter peaks in this microgrid? So we're going to look at the same 2 scenarios of the buildings, the typical building and the passive building, the peak of 4 and the peak of 2, right? Knowing that this peak is shifting to winter, which determines the total capacity required by the grid. So we're going to look at a few different scenarios. We have our baseline building with the peak of 4 in a typical centralized grid. Before we're looking at 3 of them in line, and we saw, add them up. That's the coincident peak. Now we're looking at 9. So we had the peak of each typical building, baseline building in the central grid. It sees all these together, right? The coincident peak of these buildings is 4 times 9 houses is 36. So what if we took that baseline building and we added some shifting or shedding technique? Maybe it can shift the load to a different time of day or shed half the load and set the, turn the thermostat back, things like that. So now let's say we can get about 50% out of that, reduce the peak in each building to 2. Or 2 at least coincidentally. The peak per building is 2, 9 times 2 is 18. And then what if we could take these buildings, use that shedding or shifting, so now we have a peak of 2, and then optimize when this load happens between the buildings. So now maybe only 3 buildings are experiencing that peak load at the same time. So the sum of the coincident peaks, the peak load of 2 per building that we got down to, is just 3 times 2, or 6. And the main difference between the middle scenario and the microgrid scenario is that in just the middle load shedding scenario, there'd be a central grid signal that would say, hey, the stress on the grid is high, the price of electricity right now is high, reduce load, or it would be able to set your thermostat back. On the far right scenario with the microgrid, there is that grid signal from the main utility, or maybe it's within the microgrid, but there's a manager between the buildings. So it knows when the peak of each building is happening. It can optimize so that those aren't happening at the same time. And what that can do is significantly reduce the capacity required to meet that peak once again. And then take it one step further, you guys probably get where I'm going with this. First, if you make the building passive, so we took that peak load of 4 and we brought it down to 2. In a central grid, we have the peak per building of 2, 9 times 2 is 18. Now let's reduce that by a factor of 50% again, using the shifting and shedding techniques. So we have 9 buildings with a peak of 1, so grid peak's 9. And then if we can control when this peak in the building is happening, knowing what the neighbors are doing, optimizing within this little pod, we have peak of building per 1, and the grid peak is 3 of these happening at once with a grid peak of 3. So just going from baseline with the typical centralized grid peak is 36. We implement passive building to bring down the load by 50%, implement the load shifting and shedding another 50%, and then microgrid control to optimize between the buildings. And in this, ideal scenario, what we've done is reduce the grid capacity required by a factor of 12 for the same set of 9 buildings. Right, and I know this is an idealistic scenario, but there is something to what's happening here. And if you remember that the grid peak is what directly correlates with the capacity required to meet the load of these buildings. So if you think about the cost of the generation capacity and storage required to operate the buildings on the left versus the right, you can think some of that costs from the buildings on the left could go into making the buildings on the right more efficient, controlled, and that would directly pay off. A couple more minutes, a couple other benefits, bringing generation closer to the load. So microgrids usually have generation within them, so we don't have to worry about the congestion on the transmission lines. Resilience. So if lines go down or utilities go down, microgrids can intentionally island and operate within their own kind of realm. We can improve renewable resource utilization by matching the supply available to the demand of the buildings or the demand to the supply. Optimize small areas to alleviate stress on the central grid as that decarbonizes. And one I really excited about is energy independence and lower costs and less vulnerability to utility energy pricing, but also not just utility energy pricing, but energy pricing worldwide. Providing energy independence, let's say, to affordable communities or less vulnerability to know what your utility bill might be, or maybe just self-sustaining, little communities that can operate without the external sources. Okay, solutions. I got 2 minutes. I'll be fast. Think about optimization at each level. So this is what I'm getting into, kind of the synergies. So you have passive building reduces the load, the demand, and the renewable supply required to meet that demand. Then you have GEB, the grid interactive building, enables that demand to align with when supply is available. And then the microgrid level optimizes the supply and demand, maximizing use of that infrastructure, that generation capacity and storage, and in my mind, minimizes emissions. I should mention that not all microgrids are set out to minimize emissions. Most of them, or a lot of them, are for security, energy independence, financial purposes. But I think there's a strong use case for them to minimize emissions. So all of these together are kind of tapping into each level of that synergy to reduce and optimize, grid decarbonization. I'm gonna skip this one for the sake of time. So just to kind of bring this home to think about when the grid load is high, business as usual, renewables come in first, then fossil fuel-based plants, and more needs to be called upon, right, as that load increases. If we go to passive building, first we can shed that load significantly, need less generation resources, and bring down the grid load. If we add in grid interactive efficient building technology, maybe we can replace some of the fossil fuels with energy storage or other sources, bringing down that grid load even more. And then if we can bring them all together, we can bring down the grid load even more and maybe get to the point where our communities can be run solely on renewable energy. This is my last slide. 1 minute, okay. So I just want to stress that there's a ripple effect of conservation. So even at Phius, our standards are really based on payback in terms of cost. You upgrade the building, you pay back with energy cost reduction over time. But there's a lot more to it than that. So if you consider the kind of the top level, again, like a baseline building, 60,000 kilowatt hours per year, needs a certain amount of PV to make that to 0, needs a certain amount of energy storage to meet the critical loads in the building or to kind of smooth out that PV over the course of the day. It needs a certain transmission capacity to bring that load to and from the building. in terms of excess output. If you first reduce the building load by 40%, you now need 40% less renewable energy production or PV, 40% less battery capacity, and 40% less capacity on the transmission wires. So if we think beyond the building, there is so much more ripple through the entire system of conserving that energy at one end that is generally not accounted for, and when considering how far to go with building energy conservation. And that brings me to the end, and sorry for going directly to the end / over by a minute.
Thank you, Lisa. That was great. If you have a few minutes more to entertain a couple of questions, I can extend the for those people that can stay a little bit longer. Any questions about? I have a question. Can a microgrid can be a multi-use building complex, like multi-use in terms of office, of residential, of commerce, and all that? I think the last one that's being built in Boston, the tallest passive house building, is gearing to that part.
Yeah, absolutely. So it can be any type of building mixes. It's actually better when there's diversity in the load profiles, I think, so that you have more knobs to turn when you think about, the strategies of reducing or increasing loads in the buildings to align with supply. So it could be a single building as well, as I think what you were asking. I've heard that called nanogrid. I don't know. I mean, it's the same concept, whether it extends beyond the, one building or a gang of buildings. That's where I see nanogrid versus microgrid, but yeah, same concepts.
Any more questions?
Looks like Brian has his hand up.
Thank you for this. So I guess my struggle has always been like, I'm totally sold, but why is it that, I mean, can you tell me where this is being supported on sort of a utility scale?
So the first part you said is I've done what? Solar?
I'm sorry, I'm sold. Like,
oh, you're sold. Okay.
Yeah. But so where are you seeing utilities embrace the standard? Or maybe
the Phius standard or the microgrids? The
Phius standard to start.
A lot in the Northeast. So Massachusetts, New York, Pennsylvania. Massachusetts is by far the biggest one. I can send a link here in the chat to our kind of policy database. There's actually places where Phius is an alternate path for stretch codes. But it's a lot in the Northeast, a little bit in the Northwest, and then kind of a mismatch in between. We have some in Chicago. We're getting a little bit more. A lot of the support right now is coming from affordable housing. So a big place is the qualified allocation plan for the low income housing tax credit, where the developers have to essentially submit criteria or get scored to get certain amount of points to try to get the tax credits to fund the project. And they're adding meeting passive building to get points for that. That's a big driver of a lot of projects. And then the incentive programs that are happening in the Northeast, really a lot in Massachusetts and New York. Those are driving a lot of things.
It's generally multifamily.
A lot of what we're seeing is multifamily. Yeah. There's a good amount or some in single family. There's not a ton of development in non-residential or commercial right now.
Okay. Thanks so much.
Yeah, I just threw in the chat our policy database where you can see where there's incentive programs and codes and qualified allocation plans that include Phius.
Yeah, Andy, do you want to ask a question?
Yeah, you mentioned that the conservation levels in the passive system have a financial basis. Where do you think that might change to, considering all the things that you've been talking about?
Yeah, I mean, I think even with the changes happening, I don't think the levels are too far off right now for new construction in terms of conservation paying off. I think what it might change to is you could still look at the cost payback, but considering, again, timing of energy use and integrating other features that might allow you to shift to use energy when it's cheaper or cleaner, usually go hand in hand. So maybe the optimization that is baked into the new construction standard would include the fact that hourly energy use pricing is dynamic and not flat. So we use flat rate utility prices. So the more expensive your electricity, the more you invest in conservation because it pays back. To make it more holistic, to kind of incorporate this, I think you'd want time of use for the building energy use as well as the utility price. That's just if you're thinking about operational carbon. We've gone further to think about embodied carbon of the materials going into the building. That adds a whole nother can of worms that I don't think I have time to get into today, but I think looking at it more holistically I would switch from just looking at conservation to looking at the kind of that Phius+GEB concept where it's how much can you shift your load in the building? How flexible is this building as a grid asset for the future, rather than just, did you reduce the peak load and then add PV? I think there's one step beyond that I would implement in the program.
Given the interconnectivity of the grid, can we assume that if we are in a place that is pretty much green electrons, and we assume that we are really receiving green electrons, or is it that we're getting some of the dirty electrons that are produced somewhere in the south?
Yeah, I mean, I don't know. It probably depends a little more situationally, but the closer it is to you, I think the more likely you are getting it. But I think a lot of it's just an accounting mechanism for there's this clean energy and there's dirty energy elsewhere, and you're being provided or power, whatever, you're being provided power. And so one person's paying for one's paying for another, one is accounting for it. I mean, the actual electron, we're not unless you're in an isolated grid that's only renewable energy and storage, you can't assume you're only getting electrons from renewable energy.
Maybe that was more a question for the bad people, Brian or Jen. You're still there. Okay, well, if there are no more questions, thank you very much, Lisa. I appreciate it. It was great, your presentation and the time you're taking for that, giving the bad cold that you are going through.
Sorry about that.
No problem.
Tried my best.
Okay, and thank you very much
Thank you
to everybody that entered. Again, the presentation will be recorded and we're going to be posting it at our website. So if you want to go over it again. Thank you very much. Have a good day.
Thanks, Enrique, for organizing. Lisa, thank you. That was really comprehensive.
Thank you, Jen.
Appreciate it.
Yeah,
Thank you.
Thank you. Have a nice day, everyone.